Good morning, midday, evening. Hi, Merry Christmas and welcome to Kodsnack. In this episode, which I recorded at Øredev this year, I talked to Bartosz Milewski about category theory and type theory and so many other things, like the limits of human understanding in the end. It was a super interesting conversation. I highly recommend you look up Bartosz presentations, both from Øredev this year and last year, and I think pretty much anything else you could get your hands on by him. He's a super interesting guy with lots of interesting ideas. With that said, let's roll the tape.
So, welcome to the podcasting stage, Bartosz. And thank you for a really interesting presentation.
Okay, thank you.
It was really interesting. I don't think that I caught quite everything. There was a lot of information in it.
Yes, and I skipped a lot of slides. I was going really, really fast, like starting slowly, and then wham.
So your subject this year, or the title this year was Programming with Math.
Yes.
Right.
Very generic title.
Yeah.
I knew I would be talking about something related to math, but I wasn't sure what.
Yeah.
Depending on which direction, I was pushed by external forces.
Yeah. So how long before the actual event did you decide on the content?
Maybe a month ago.
Huh?
Yeah.
So this is right.
That was, it was sort of crystallizing slowly. It's like, what are the interesting things that I can say? It's like, what is fascinating for me at the moment?
Yeah, and so currently it's this, what would we call it? Like a
type theory.
Yeah, improving the commonalities between
between logic, programming, category theory. Yeah. I usually talk a lot about category theory, but this year I decided I'm going to tone down the category theory and go more into type theory.
Yeah. So what brought you to that direction? What were the starting points that led you to the subject?
Where should I start? It's like prehistory of all this. So historically speaking, I started as a sort of studying mathematics in high school, and then I went into physics. So I'm really comfortable with math.
Yeah.
But then I went into programming, and that was completely different, right? Although the same sort of problem-solving skills are useful in any area, really.
Yeah,
right.
That's true.
But so once I learned programming, I started thinking about more abstract things. Like I was doing C++.
Yeah.
And then in C++, like what's the hardest thing in C++? Template metaprogramming, right?
Oh, yes.
So I went into template metaprogramming, got excited about writing all these templates, and then I discovered that the template language is really a functional language.
Mm-hmm.
Because there is no mutation at compile time.
Yeah.
Right, so all these algorithms that people were writing, they were writing books about template metaprogramming. Actually, I knew these people who wrote these books, and I talked to them, and their background was in functional programming.
Oh, okay.
So once I knew that, I started learning a bits of Haskell, and then discovered a new franchise. It's like, okay, I read something about Haskell. Translate it into C++, write a blog post, It's like, huge discovery. Wow.
Market. Yeah,
nobody's done that before. But then I cut the middleman and I decided to go directly into Haskell.
Oh, yeah.
And then once in Haskell, it's like, what's the hardest thing in Haskell? Okay, well, there are these functors, monads, all this stuff. Where do they come from?
Yeah.
They come from category theory. Okay. I have to figure out category theory. So I started studying category theory.
Yes.
And then I decided, okay, category theory is really, really hard. It's like you read these papers or books, you know, there's like McLean's category theory for the working mathematician, right?
Yeah.
And it's like an encyclopedia of category theory, but it's written in a style that's really very difficult to understand. It's like I read a few first sentences, and it took me, I don't know, about a month to understand them.
You know? That's a tough start. Some people would give up.
Yeah, no, I don't give up.
No,
it's like I'm like a pit bull, you know. It's like I grab on something and dig into it, and eventually it got easier. But the problem is that mathematicians who write category theory, they are just like really, really advanced mathematicians. So they know everything around in mathematics. They already studied topology. They started algebra. They studied this and that and that, and they give lots of examples. You know,
and
here's how. This is an example of a functor that goes from a group to an algebra to stuff like this, and so for normal people, right? And this is like I don't understand these abstractions because I don't know what they are abstracting over. I would have to first understand all this stuff, right?
Yeah.
But I discovered that it's like. I can have examples from programming, and they are much easier to understand for programmers, right? It's
Makes sense.
So a functor is this, and this is how you implement it, and you can compile it and you can run it, okay? And it's like, okay.
It makes more sense that way for us.
Right, and like examples of monads, okay, well, it's a list monad or maybe a vector, a tree, a function, it's like, okay, these are nice examples. I can live with these, right? I can go through all these examples and then I can formulate some kind of abstraction of what a monad is based on these examples rather than topology or algebra.
Yeah.
Right.
So it sounds like a big part of the challenge is that the category theory stuff was written for people with a different background.
Exactly.
And sort of bringing all that context. Has that changed? Are there like more accessible sources for programmers now? Because it seems like category theory is sort of slowly becoming a bit more, maybe not mainstream, but at least.
Well, so I think what happened is that the idea of category theory is not that difficult.
No.
It's just because it was done by mathematicians, they made it difficult.
Yeah.
Right? They made it hard because they wrote for other mathematicians.
Yeah.
And mathematicians are just... I come from a physics background. So in physics, we have these people like Feynman, who was able to explain quantum theory to a random person in the street, right? Yeah. So it's like it's a matter of pride that you can explain really hard concepts in simple language. Mathematicians don't have this. I don't think so.
No, I never heard of it.
They think like the harder it is to understand, the better.
Yeah, and everyone should understand all the background.
If you don't understand it, you're just stupid, right? So it's a different culture, I think. I think it's changing. There are some mathematicians who really care about explaining things.
Yeah.
And actually, I had contact with some mathematicians while writing my blog posts and working on category theory. I contacted several mathematicians, and they were extremely happy to help me.
Oh, that's nice.
They actually, they would write proofs for me, just explaining stuff. And I would ask them questions, and they would say, okay, this is how it works, and so on. They were very happy that somebody was from outside of mathematics was interested in what they are doing, because people are just like ignore mathematics.
Yeah, I mean it's easy to fall into, isn't it? Like,
Yeah,
I hear mathematics and some term I don't recognize, and then I sort of assume that this is probably too hard, and there's probably no one who can explain it to someone with my programming background or something. But that's good to hear. It's good to be wrong.
And I was really surprised or even shocked, It's like when I started doing category theory for programmers, I started writing the blog, and now it's published as a book. I thought nobody would be interested. And then suddenly there is like a huge interest in category theory. People are reading this and they are watching my videos on YouTube. Programmers trying to figure out category theory, and they find it fascinating.
Yeah. So why do you think it is that it's become, I don't know, discovered right now?
I think this is like a different phase of mathematics. It's like we are taught math in school that is really boring and repetitive, and they teach us how to, multiply and divide things for days and months and so on. While we have calculators that can do it in a fraction of a second, right? Like, what's the purpose of this? And it's like most people say, I will never, ever use this stuff. I mean,
no.
Like solving a quadratic equation. I mean, how many quadratic equations do you solve every day? or a year per year? None, right? So this is like useless knowledge. And it's difficult and it's not fun. Whereas, and category theory suddenly, when you look at it from the perspective of a programmer, this is like, oh, this is cool. This like gives me new insights, like, and actually helps me formulate solutions and problems and solutions, right?
Yeah.
Yeah.
But, so was it just? I mean, do you think did something happen that sort of made programmers start to discover category theory now? Was there some kind of...
maybe, I don't know. Maybe this is because nobody tried it before, right? So it's like, and suddenly, if there is a person who can actually explain this stuff in simple terms in terms of programming, maybe that's the breakthrough. Maybe maybe there was this gap between programming and math, and I was sort of able to bridge this gap.
It's interesting how.
But I didn't realize that there was such a need. You know, it's like I liked it myself, but it's like it turns out people need this. Yeah. There's demand.
Exactly. Does it have anything to do with the kind of problems we're trying to solve or something like that?
I think so. I think category theory describes exactly the type of problems that we are trying to solve in programming. Because the idea of category theory is, it started from mathematics, but it discovers structure. Right? It's like we have all these mathematical theories, and they were developed separately, independently. Each of them used a different language, different notation, and so on. And then there were these few mathematicians that were looking at these different areas of mathematics and saying, well, there is a lot of commonality between them. There is like an underlying structure. Right? They discovered the structure and they formalized it, right? And this is the structure that describes a very simple thing that's like so basic to everything we do that when we face a complex problem, we split it into simpler problems. We decompose it. And then we solve these simpler problems and recompose them. And this is like, in the nutshell, this is what category theory is. How to split things and how to compose them.
Yeah.
You know, so it's like the science of composition, right? And it's like if you talk to programmers, you know, this is what we do every day. Every single day we face difficult problems, and then we split them into sub-problems, right? We create a program from directories. In directories we have files. Inside a file we have data definitions. We have function definitions, right? Why do we use functions at all? Why don't we just write, you know, one huge program with lots of go-tos and so on, right? That's how we started, right? A long time ago.
Yeah.
But then we discovered that no, this is like impossible to deal with. We humans have to structure things.
Yeah, we need it.
We need it. And category theory just provides this abstract tool for telling you what are the different ways of splitting things, of decomposing them.
Oh. So do you think the way we write, I mean, both the way we write our programs and our programming languages, do you think they will change significantly as category theory becomes more understood by developers?
I think so. Yeah. Yes, definitely. I think mathematics is the future. It's yes. I mean, you can see that programming is getting more and more mathematical, and we are just like always trying to find a better language that would be describing things more abstractly, because I mean, who wants to program in assembly language, right?
Yeah.
I mean, yes, sometimes you have to get down to the metal and
yeah, it happens.
Right, it happens, but presumably, you know, this stuff can be automated.
Yeah.
You know, it's like we have all these neural networks, artificial intelligence. I mean, if you can program an AI to win a Go match or chess, right? Why can't we use an AI to optimize our code, to translate it into assembly language so that it's like better optimized than whatever a human could do?
Yeah.
Because there are some very, very strict rules. It's sort of like playing chess, you know, but with machine instructions. You know, what happens when I do this instruction and followed by this and so on? What if I rearrange them? You know, it's like you're playing against an opponent that's the execution time and resources that the program is using, and you want to optimize it. So computers are very good at optimizing stuff. They should do this.
Yeah.
But somebody has to tell the computer what to optimize, right?
Yeah.
What is the idea?
Yeah.
What is it that we want? And we have to formulate it in a way that's precise enough so that it can be translated by the computer into a program, but abstract enough so that it doesn't take us forever to explain it, right? It's like explaining the computer step by step, you know, first you move this to here, then you move this, then it's like do it forever, and you know, this is like a very, very tedious work.
Oh yes.
So we want to say, well, here's an array, sort it. Okay.
Exactly. Go on.
Yeah.
Do you think do we need like even higher level languages to work better, or are the languages we have now about the right level?
I think the ultimate high level languages is the language of math. Yeah. So we are getting, well, so there is a convergence really. You know, it's like mathematicians started discovering computing as well. Not only
that's an interesting.
Yeah. I mean, there is like a mathematical proofs are getting more and more complicated, right? I mean, they sort of did all the easy stuff in the 19th century, right? maybe beginning of 20th century. Now it's the hard stuff that remains, right? Like the proof of Fermat's last theorem is so complicated, right? It's like studying this proof takes years, right?
Yes.
So how do you know this proof is correct? Maybe he made a mistake, and actually, the mathematician who made this, he made a mistake, and people read it and pointed out, and he had to fix it. Took him a few months to fix it, but eventually, like, we believe that this proof is correct, right? But it's sort of by acclamation.
Yeah.
Like a bunch of mathematicians say, "Yeah, I've read it, and I didn't find an error." So it's like sort of like when we are writing software and we have a test suite, right? And then we say, okay, it passed all the tests, so I guess this program is correct, right?
It's not proven wrong yet.
Test-driven proof development in mathematics.
Makes
right?
sense.
So, but there were cases where people discovered errors in mathematical proofs years afterwards. You know,
yeah, of course.
And so this is really frustrating. So it would be great if you could like formulate a proof in a more formal language.
Yeah,
I mean, we think of mathematics as a formal, not really. Okay,
it's a different kind.
There is a lot of hand waving in math as well.
Yeah, it's just done with nice symbols, so it looks.
Yeah. So they started like designing a more formal language. It goes back to the last century, but it's like sped up recently because we have now better, faster computers.
Yeah.
So like mechanizing proofs, mathematical proofs, is becoming more and more important.
Interesting.
And so what they found out, mathematicians, is that if you want to formalize mathematics, well, you have to start somewhere, right?
Makes sense.
Like, so what are the foundations that you start with? They started digging into the foundations, and they discovered that even these foundations are sort of crumbly. You know, it's like we don't really know where to start. Should we start with set theory, or should we start with category theory, and so on? So there is this completely new trend recently. It's called Homotopy type theory that is trying to revolutionize the foundations of mathematics. And it has a lot to do with this idea that you want to formalize proofs using computers.
Is it looking promising?
Yeah, it is looking promising. It's like a very hot area of research right now. Yeah.
So it's not proven to be correct is a strong word, I guess, but
no, it's still under development. Yeah, and the homotopy type theory, as the name suggests, has something to do with type, right?
Yes.
Types. This is why.
This is familiar.
This is why I'm so interested in type theory. It's an outgrowth of type theory.
Wow.
So type theory in mathematics is like foundational. It's a very, very strong foundation of mathematics. And it so happens that we use types in programming.
Yes.
And the types in programming were invented for completely different purpose. You know, it's just sort of like to discover bugs, you know, it's like prevent people from making stupid mistakes and so on. But it turns out that these types that we use in programming, they actually correspond to types in type theory.
Oh yeah, and it's sort of a coincidence or like parallel evolution. Is
something. Is that a coincidence or not? Right. And so it turns out that there are even more areas of science that follow the same pattern. So it's not only type theory, but it turns out that logic, which is a very, very old branch of mathematics, right? that logic is actually equivalent to type theory. That it's essentially the same theory, but using a slightly different language and notation. So this is called the Curry-Howard isomorphism between type theory and logic. And then people realized, okay, but there is also category theory. Well, there is a branch of category theory that's totally isomorphic to type theory, or is a model of type theory. You know, these Cartesian closed categories, they are actually equivalent to logic and equivalent to types, to type theory. So it looks like, is this a coincidence that the completely separately discovered branches of mathematics are essentially identical? So this is what I was talking a year ago, you know.
I was
right. I had a talk here at Øredev about
was fascinating.
why the sort of my philosophy, why these things are the same.
Yeah.
They are the same because this is the only way we humans can understand nature. We have to look for patterns and how these patterns are combined, composed, decomposed, and so on. So it's like all our science, mathematics, physics, is just about composing and decomposing things. So no wonder we discover the same things over and over again, because there are so few ways of composing things.
Yeah, we're just looking back at how we work ourselves all the time. I mean, it was a fascinating talk as well. It's sort of frustrating in a way. What if we could break out sideways somewhere or something? But
I think this is like the property of, well, maybe even property of life itself, that in order for life to exist, there has to be a way of modeling reality inside an organism, inside a brain, okay?
Yeah.
But even before the brains, you know, a bacterium reacting to the environment, it has to have some kind of model of the environment, which means that the environment, the nature, there has to be a way of simplifying it, abstracting some stuff, right? So as long as it's possible to take some part of the environment and abstract it into something simpler, sometimes even like binary, you know, there is light, there is darkness, light, darkness, you know, it's like, okay, so there's one property of the environment that can be abstracted, right?
And we build up from there.
So if we can do this, you know, then life can exist because it has to react to the environment. Therefore, it has to have a model of the environment. Like, you know, at some point we abstract stuff like, oh, here's a predator, we have to run away. Okay, here's food, we have to run towards it, right? And so on. So it's like this abstraction of predator and food. Basic, very, very basic abstractions. So if we couldn't make these abstractions, we wouldn't be able to live.
No.
Right? So it's like anthropic principle, ultimate anthropic principle, you know, it's like life exists in an environment that's decomposable because life can only exist in a decomposable environment. You know, if there is an environment that's not decomposable, there is no life there, so there's nobody to talk about it. Right?
And if we saw something like that, would we even be able to grasp it?
I think we see this. We see this we see this in physics. You know, in quantum mechanics, we see things that are not decomposable, and we desperately try to decompose them. And we say, okay, a quantum particle is, well, it's either a particle or a wave. Okay, because particles are decomposable. You know, it's like a system of two particles consists of one particle and another particle.
Yeah, we can work
Waves are decomposable because they interfere. It's like these are the decomposable things we know. So we have to use these tools. So we say, but a quantum particle is neither particle nor wave, right? It isn't. So we have to squint left, squint right. Yeah. Is it particle? Okay, now it behaves like particle. Is it a wave? Now it behaves like a wave, but it's neither.
Yeah.
And then we go deeper into physics. It's like you have quantum mechanics and you have gravity, right? And we would like to decompose quantum mechanics on the left, gravity on the right. How do we compose them back? We don't know.
No.
Right? and of course, physicists and mathematicians are saying there has to be a way. We'll eventually get there. But maybe not.
No.
Right?
No.
There is no guarantee.
No. Yeah, and that's such a fascinating thought in itself. I mean, that's sort of contrary to everything we want to think. Like we can understand this, but
it's not a very popular thought because, like, if you're a physicist and you think, okay, there are certain things that we'll never know, okay, that's like defeated.
Yeah,
it's like no.
But I mean, it makes me wonder if we were to accept that as some kind of fact to deal with, I wonder if could it affect maybe something day to day? Would we write programs differently if we thought that composition and decomposition had limited use? Could we solve programs differently then somehow? I don't even know how to think about this, but
I don't know. I think we have to compartmentalize this and just say
that's what we do.
We know how to deal with decomposable things. Let's deal with decomposable things, and that's it.
And leave it to someone.
And there is a lot of work to do with decomposable things.
Oh yeah,
still,
there's still a lot.
So it's like we will not run out of possibilities of writing new programs and improving our lives and saving the planet and so on. But we have to know that there might be stuff outside of our reach.
Yeah, and if there is such a thing, could there even be something else in this universe that could deal with that, or would that be impossible in itself?
Well, if there can be something like this, then definitely we cannot imagine it, because we
wouldn't even notice.
The only tool that we have to imagine things is our brain, and our brain works by decomposing things.
So it's.
And computers work the same way.
Exactly, because we have to build it with our understanding.
It's not like we will create this wonderful artificial intelligence that will be able to do things that
we can't imagine.
Yeah, well, maybe it will do, but it will still be bound by compositionality.
Yeah,
there is no escape from this.
It's kind of a bummer, but it's also super interesting. This has to have.
Effects. This is wishful thinking, right? But we cannot live our lives by wishful thinking.
No,
we wish everything were decomposable. We wish that there was a theory of everything, right? Like the physicists always dreamed of this theory of everything. And when I was younger, I also thought, when I'm older, there will be a theory of everything. We'll unify gravity with quantum mechanics and.
There is a simple solution.
Yes, but why? Why would there be a simple solution?
Exactly.
It's that would mean that this universe is simple for a purpose, maybe for us humans, monkeys to understand. I don't think so.
I like that conclusion in last year's talk. either it's not it might not be understandable, but that means it's not a simulation, which is encouraging.
Yes, yeah. That's the encouraging part.
Yeah.
It doesn't look like it is a simulation.
Yeah.
The simulation would be totally decomposable.
Yeah, and that's something we could reason about.
Yes, yeah. So if we find that the universe is not decomposable, then we sort of prove that it's a proof that it's not a simulation.
Yeah.
It's real.
Yeah. Which is good. Nice to know.
Yeah. So there's a positive side.
The universe
to it.
could well be real, as it looks right now.
Yeah.
So yeah. So what? Do you have any idea what your next interesting area might be? What you might be talking about next year? Is there something starting to catch your interest?
I don't know.
I'll just have to wait a year and see.
Yeah, I wouldn't be able. Last year, I wouldn't be able to predict what I would be interested this year. So
that's part of the excitement.
Yeah.
But it will probably be something like building one step at a time. Yeah. Yeah. Thank you so much for taking the time. This was super interesting.
All right.
Great.
Let me put it this way, Mr. Raymer. The 9000 series is the most reliable computer ever made. No 9000 computer has ever made a mistake or distorted information. We are all, by any practical definition of the words, foolproof and incapable of error.